Good morning, eighth graders. So we are finishing up our astronomy unit. So we have talked what is gravity? We have talked what are our planets, what's within our solar system, and even slightly beyond into our galaxy and universe. Now we're going to take both of those really big concepts and we are going to mush them together and explain why does our solar system look the way that it looks? There is a reason why the four inner planets are very, very small and rocky versus the four outer planets are very, very large and gaseous or ice-ridden. Um, those sorts of things. So we are working with middle school Earth Science Standard 1-3, 1-2, and middle school Physical Science Standard 2-4, which essentially, all in all, by the end of today, you should be able to start actually putting all of this together. What you'll be able to do is analyze and interpret data to determine the scale of objects within our solar system. You should be able to develop and use a model to describe the role of gravity in the formation of our solar system. So explain why things are the way that they are. And then finally, you should be able to start putting together a claim that is supported with evidence and reasoning to demonstrate that gravitational interactions are attractive and depend on both the mass of the object as well as the distance the objects are from one another. So let's start kind of putting this together. You should be sure to have these notes in front of you, your 3.7. And we're going to do this more as a whole group sort of style. So if you are listening to this within class, study hall, whatever, um, make sure you're being respectful of your champ's expectations, please. So let's have a quick little review. So gravity is just that fundamental force that has been always with us since the moment we became a thing here on Earth. Gravity has been placed upon us. To where that's why we don't feel gravity. Okay. In class, I give the example of like you don't realize your hair is playing such a role on your neck until you chop it off. Okay. Then you're like, oh, my neck feels better. That sort of thing. That's what gravity does to us here on Earth, where we don't feel it until it's gone. So it is the attraction force between two or more objects with mass at a distance away from each other's centers. So us compared to the center of the Earth, the moon compared to the center of the Earth versus the center of the sun, those sorts of things. Um, and then we have Galileo Galilei, who found that objects of different masses still fall at the same rate. So it had to be due to this constant force that we then named gravity. Isaac Newton then went on to develop the law of universal gravitation and developed his three laws of motion because of gravity. And then just understanding that gravity is what essentially has shaped our solar system, not only as these spheres, but also in the roles that they play within separate um, objects and why they are where they are and all that kind of fun jazz. So that is just a quick little review on what gravity truly is. So let's talk about the gravity in our sun. Okay, we know that the sun is our most massive object within the solar system. The sun contains 99.8% of all of our solar system's total mass, meaning that all the planets, moons, asteroids, comets, meteors, or meteoroids, and all of those added together is only 0.2% of the rest of the mass. So, because the sun has such a large mass, it allows for this really strong exertion of gravitational pull. It holds everything in its orbit because of the amount of gravitational pull it has. The sun's gravity keeps our planets and other objects in the orbit that they are. So it goes Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune because that is how the sun has its grasp on all of the planets. Okay, So without the sun, our next largest mass basically is Jupiter. So could you imagine if Jupiter were our center of our solar system rather than the sun? Okay, would it have enough mass in order to hold all the other planets, or would other planets start to just drift away? Things that I'm going to ask you today are going to make you think of what ifs. Okay, so planetary orbits. Let's do a quick little review on some vocab though. Okay, so we know that planets orbit the sun in an elliptical pattern, not an eclipse, an ellipse. And an ellipse is, let me make sure I select a color that'll actually show up. An ellipse is this like oval shape curve. It's not perfectly circular. It goes a little bit oval. Okay, now when we talk about orbits, we are talking about revolution. So remember, we have to think that the sun's in the center. The sun looks a lot cuter than that though, but this is what you get with my mouse. Okay, so we have the sun, and then all of the planets are revolving or orbiting the Earth in a counterclockwise manner. Then we have the planets doing their own rotation, which is them spinning on their own axis. Okay, I just want you to make sure that you have those kind of set. So when I say either orbit or revolution, it's the same thing. Rotation, however, not. Okay, so gravity is what keeps these planets within their orbit or within their revolution around the sun. So because of proximity and how far it truly needs to go, the closer the planet is to the sun, the faster it orbits around. That's why Mercury only has an orbital revolution that's like 3 months, okay? Versus, say, Jupiter, who takes 9+ years. Okay, I think it's 9+ years. Don't quote me on that number. But either way, we for sure take 1 full year. That's 12 months. Or Mars takes like 2.5, almost 3 years to go around the sun at the same time that Mercury is only taking 3 months. So that is because of gravity. All of this is because of gravity. Okay, now, like I said, I'm going to ask you a lot of what if questions. So, scale and position of objects in our solar system. So, let's talk about small versus big. We have started talking about how the 4 inner planets are very, very small in relation to the 4 outer planets that are very, very large. Earth being one of the largest inner planets, and I mean, we can technically travel around the Earth in just a short time. But with the 4 inner planets, we have to ask ourselves, why are they so small? Because the second you get outside of the asteroid belt, now you get these massive planets. Well, one of the main reasons why the inner planets are so small is because if they were any larger, as we know with gravity, the larger the mass of each object, the stronger the gravitational pull. Okay, so if you have a thing like the sun, and then you have a thing like Jupiter, they are going to have so much gravitational attraction to one another that they're going to want to come together. Okay, versus you have a thing like Earth and a massive thing like the sun, and we just kind of stay where we're at. Okay, it doesn't feel like it needs to pull us in, but we're also being pulled in another direction. And again, gravity. We are essentially between Earth and Jupiter. Sorry, let's make sure you can see that. Jupiter, because they're both pulling us in opposite directions. That's why we stay in our orbit. So if things were larger, the closer to Earth, they would just be closer to the sun, they would just be engulfed within our sun. Now, why are the inner planets rocky? Well, the idea behind this is that they're so rocky because as things were forming shortly after the Big Bang, okay, the sun is so massive that it essentially pulled all the lighter elements it could, oxygen, argon, carbon dioxide, hydrogen, helium, very light elements, started pulling it in to where all that was truly left for our inner planets were these super heavy elements, carbon, iron, silicon even. They're heavy, okay? All of our gases are very light. That's why we don't see them, but we can breathe them in. We know it's around us versus can you breathe in a chunk of carbon? You shouldn't. Okay, things like that. So because of how close they were to the sun, the temperature essentially took all of the light elements and absorbed them because it could be pulled away from these planets much easier. But these heavier, rocky sort of materials were left behind. So we are left with a mainly carbon and silicon like sphere just hanging out. If you look, Mars doesn't even really, or no, sorry, not Mars, Mercury doesn't even really have an atmosphere and how close it is to the sun versus Venus, where you get just slightly further away and it has a very well developed atmosphere. Now, granted, too well for any life to be able to live upon it, but then you go slightly out and you get us. We have the Goldilocks of all atmospheres, where it's just thick enough to hold in all of the elements that we need in order to survive, but light enough to where others can escape if necessary. So that sort of a thing. So this is all because of that gravitational pull from the sun. Now, what if questions? What if you change the position of Venus and Jupiter? Okay, so we have to think about the size of Venus versus the size of Jupiter. Venus is about the same size as us. Jupiter is massive. Okay, so if you change the position of Venus and Jupiter, you flip them around, what starts to happen? Well, Jupiter will be way too close to the sun, and it's far too large to where their gravitational attraction gets sucked in with one another. Then we are now losing that additional extra mass on the opposite side of the sun, keeping all of the planets kind of in line to where we can then only assume after we lose Jupiter or its placement of Jupiter, we then lose the ability for a majority of the outer planets to stay where they're at. We lose the asteroid belt from being where it's at. The asteroid belt is only where it is because you have the sun's gravitational pull and you have Jupiter's gravitational pull, and they're essentially holding on to all of those asteroids and keeping them in their place. Asteroids very seldom leave the asteroid belt, only if they're knocked out by something else, or else they're just a bunch of rocks floating in this ring. So if we were to switch Venus and Jupiter, we would not see the solar system we have today. We would not have all of these planets. We would not have all of these other structures being held in place because of where our planets are. Okay, so that's why we can tell that gravity has such an impact on the creation of the solar system, because everything tended to work out perfectly. Okay, I'm hoping this plays in here. If not, I am going to link it in Schoology, but it's essentially to kind of show, if you were to imagine, let me get my little laser pointer, if you were to imagine, can't even go over it, this magnet, this large one where the fingers are currently at, as say the sun, and you have this large magnet down at the bottom as say Jupiter, then you'll see the impact that this one in the middle has in its position due to the gravitational pull of both. So it's just a short clip. I'm hoping it's gonna play. If not, like I said, pause this video, click into it quick, and you can see kind of like what's going on. So hopefully if it's playing for you right now, you can see that the sun is being moved slightly closer to what would be considered the Earth, or that middle magnet. And that magnet is moving slightly, and especially the closer you kind of get, but it's not leaving. That's because of the gravitational pull that is happening within both the sun and Jupiter. So gravity and moons. We would not have moons without gravity, okay, or a moon. Well, in our case right now, 2024, we have moons, but the moon's orbiting planets is because of the gravitational pull of the planet as well as the gravitational pull of the sun. Our moon is much, much closer. So remember, the shorter the distance, the stronger the gravitational pull. But the larger the mass, the stronger the gravitational pull. So the sun is far enough away, and as large as it is, that it is trying to pull the moon away from us, but it stays where it's at because it's closer to the next largest body, and that's Earth. So our moon is held in place because of our gravity. It then starts to affect things here on Earth. We get tides, high tides and low tides. And yeah, the sun plays an effect on our tides, but much, much less than the effects that our moon plays on our tides. So every day we are faced with high tides and low tides because the moon is essentially trying to pull the water away from the surface. That's what creates a high tide. And then when the moon's on the opposite side of the Earth, or we've rotated away from it, then it's trying to pull it from the other side, bringing that front side down. Okay, we do get things like spring tides and neap tides when you get into the full moon or new moon position and we're lined up with the sun. Okay, because then you have both forces pulling on one side together. So it makes the tides just a little bit stronger, a little bit higher, or a little bit lower on the opposite side. Now, some of our planets, as soon as you get away from us, have multiple moons. Jupiter has 79 known moons. Okay, Jupiter and Saturn have the largest amount of moons, and we have to think of what their gravitational attraction is. They're gigantic planets. Of course they're going to be able to handle more moons, but with where they are, their distance from the sun, what would tides look like on Jupiter if there was liquid of some sort? Okay, you have 79 moons trying to pull. Would it make the tides higher? Would it make the tides really wonky because you have 79 around this giant orb trying to pull in different directions potentially? What happens if you get a couple moons that are lined up in the same sort of like line like we get with the sun, moon, and Earth when we have our spring tides? It's things like that. It's like, what would it look like? And I'm pretty sure I wrote that into your notes. I want you to think, what would it look like of the 79 moons? What would Jupiter's tidal system look like? Who knows? So, just random thoughts. Now, gravity has a control over smaller objects, such as asteroids, comets, meteors, all that kind of stuff. So they're affected as well. Remember, asteroids are those rocky objects that are orbiting the sun, typically within the asteroid belt or the Kuiper belt. But then we get comets who do this really fun thing. So if we have our sun, that's probably as best of a circle as I'm going to get today. Okay, so we have our typical sun planet orbital revolution. Okay, But then you get things like comets where they come in super duper close and then they just whoom all the way out there. And yes, I make sounds. Okay? So, why is it that these comets have such an obscure sort of ellipse that goes so much further away from the sun, but yet it gets super duper close? Okay? We have meteoroids. So these small balls of rock, similar to asteroids, just smaller, that get captured by moons and planets. And as they enter into our atmosphere, they burn up. They hopefully turn into sizes of like grains of sand, but sometimes they don't. They stay a little bit larger and we get like massive craters. That's why our moon looks the way it does, is because all of these meteoroids that entered its atmosphere and just, okay? We have our asteroid belt region. Okay, we've already kind of explained this, but that region between Mars and Jupiter is only where it is because of the sun and Jupiter pulling on it. Okay, imagine like those cartoons where you have the person in the middle, excuse me, and someone on either end pulling them, and they're just kind of sitting like this, back and forth. Same thing is kind of happening with the Kuiper belt outside of Neptune. You have the sun pulling on one end, and then you have the rest of space, okay, trying to pull it the opposite way. So without gravity, these would not be where they're at. Gravity is crucial to space exploration. We have to understand what gravity is and the roles that it plays so that we know how to launch rockets and satellites out of our orbital grasp into space so that we can study it. We have to use things like gravitational assistance, understanding how gravity works so that using a planet's gravity, we can speed up and slingshot that much further. We were having a discussion as a team last night about how the amount of rocket fuel necessary to make space travel like an option is far more massive than what we are actually using. Why is it that we can get away with much less? Because we use things like a gravitational slingshot, where we essentially launch a rocket on one side of the Earth that isn't necessarily in the direction we want to go, and it can get picked up by Earth's orbit and then slingshot and like fling out using much less rocket fuel. So we can get further without taking up more space in order to provide enough rocket fuel to get to where we need to. So that our satellites, we would not have telecommunication. We would not have the internet and things like that without our satellites staying where they're at. Why is it they don't go zooming off into space or come crashing down to the Earth? Granted, you want $1 million idea, figure out a way to clean up the space junk, all of our extra satellites that are essentially just dead old pieces of technology. How are we going to clean that up from our atmosphere and our gravitational pull so that when we need more advanced telecommunications or whatnot, we have space in order to put the satellites out there? Just one of those things. And if you make it rich, remember G. Okay? Because I'm not rich. Okay? We talk about the International Space Station, and it's in this perfect orbit where it's essentially free falling, but not falling. So it stays where it's at in order to allow for astronauts to feel this weightlessness in order to keep the actual station where it is so that they can explore, so we can learn more about potential space travel and things beyond that. Gravity has a role in all of this, and I feel like a broken record saying that, but it truly does. Without these understandings, we would not be where we're at today. We would never have put a man on the moon. We would never have been able to launch satellites to go and explore other planets, to hopefully go explore other solar systems and galaxies in the future. And speaking of that, we got to start looking beyond just what is in front of us. Okay, so gravity and beyond our solar system, we have to have the understanding that gravity affects all galaxies, not just the Milky Way. Okay, we know obviously at the center of any solar system there's a star. Okay, any solar system we've been able to observe, there is a star of some sort there. So what would be at the center of our galaxies? Well, it's got to be something bigger than a star, because it would not be able to hold the millions of galaxies it does within its space. The picture that is like slightly above my head is the Milky Way galaxy, and we are just one of those little spots of light way even out here. We are far away from the center. So what is holding us where we are at? The prediction, and I believe it has been proven, don't quote me, but at the center of our Milky Way galaxy is a massive black hole, to just show you how absolutely ridiculously strong a gravitational pull can be. So much so to where gravity is even bending light. Okay, it's called gravitational lensing. It's similar to where if you took a glass pyramid or triangular prism, and you shine a white light through it and it breaks off into the rainbow. That's essentially what black holes are able to do as well. Now, gravity, as I have repeated and repeated and repeated, is so important to understand. It's without a doubt because of these four main points. Without gravity, we don't have the shape of our solar system. We don't have elliptical orbits. We don't have spheres. We don't have just the basic necessity for us to be a solar system. Without gravity, we would not be able to keep our planets and our moons and other objects within our orbit. And without the sun, we especially here on Earth don't get the light, the energy, and the necessary heat to keep us alive. And then 3, gravity affects our tides, space exploration, and galaxies. Without gravity, we not only wouldn't be here, but we wouldn't be able to do certain things. Yeah, no, tides, do they affect us here in North Dakota? Not even a little bit. But do tides affect any of our coastal states, any of our coastal countries? Completely. Does it affect us being able to actually get out into space and see what else is out there? We as humans are curious animals. So to be pigeonholed and stuck on one planet in one place is just not our habit. And then our galaxies. To know that there could be galaxies out there with the potential life or life-sustaining planet. Okay, we need to be able to get out there and go see these. And then finally, without gravity, the universe as we know it just really wouldn't exist. So it makes you then think, I want you to think about this. How would life be different without gravity? Now let's put it in the idea of how would life be different without gravity? And we're still here on this planet. We as a species are still very functioning. What would be different? Okay, I just want you to think about that, because it is a constant that we kind of take for granted. Okay, I'll admit, I thought at the beginning of this year, the way that I taught gravity was just dropping a pen and that was sufficient. But as I've gone through and determined that you all need to know more, which means I need to know more, I have found a love and curiosity for gravity to figure out what is it. Now, granted, am I going to be the next Stephen Hawking or Hawkins? No, I am not smart enough for that. But to sit here and say, okay, I can sit in my desk. I can use the internet whenever I want between my phone, between the computers, things like that. I can get up, I can carry my son and all of this sort of stuff. We're going to go to a trampoline park tomorrow. Why is it that we can bounce around but still come back down to earth somewhat safely? Okay? Things like that. I want you to think about that because that is what's going to impact everything you do, and especially your assessment. So, if anything, I just want you to ponder it long enough to get through your assessment. Okay? If you have any questions, please ask. Am I going to have the answers? No. Am I willing to look them up? Completely. Okay? But ask your questions. Okay? Awesome. That was a lot of me feeling like I just repeated myself over and over and over again. So hopefully you got something out of this. Let me know if you have any questions. Thank you, 8th graders. And Declan, if you are watching, thanks. I love that you support your auntie. Okay, fabulous. I will chat with you all later. Awesome. Bye.